Start some content now, and this is Elements of Electrical Engineering, which is the non-majors version of circuits. So we're going to start with circuits. So what the heck is a circuit? So a circuit is an interconnected electrical component. So interconnected electrical components. When I gotta get a different piece of chalk. That one feels better. When I do terms that are terms we're going to be used, I'm going to follow this format for each term, and that I'm going to say what the name of the term is. So we're going to start with introducing what charge is, and then I'm going to talk about the symbols. And for these, we usually have a big symbol and a little symbol. The big symbol is something that's not a function of time, or if you see it in another equation, that's a little symbol, be little q of t, that's a function of time. So either one means charge. And then I do units. And for me, I like to put units in square brackets. So it's the unit is a coulomb. So for this lecture, these are my coulombs. We'll have some ping pong balls moving around in here. So this is a coulomb. He's a unit of charge. And moving charge around is what becomes circuits. So charge in motion leads to energy transfer. So we've got to talk about these coulombs moving around. And when you talk about moving them around, it's usually how many of them are moving around in some given amount of time. So if we look at the time rate change of charge, that gives rise to something that I'm sure you've heard before as a word, which is current. So the next item I'm going to introduce is current. And he's either big I or little I of t if he's a function of time. His unit is an amp, ampere for the full version, which is the time rate change of current, so he's a coulomb per second. To say this in like the mathematical expression form, we'll do it up here. So current as a function of time is the time rate change of current, so the derivative with respect to time of current, or if you look at it the other way, what is current? We just go all the way back in time, all the way back to negative infinity, to whatever time we're living at right now of the integral of our current. So this is how I'm going to introduce symbols. We'll have some equations that are like this that I derive along the way. Equations that you end up using a lot, I'll box. When we have exams, there will be a formula sheet provided to you as part of the exam, which you'll see ahead of the exam. So you don't bring your own formula sheets with you. And it'll usually consist of all the equations I've boxed along the way as we're going along there. So we have current, and this is the part that bothers some people right now, but you just have to go with it. So circuits convention, when we talk about things flowing, is the movement of positive charges. So our current flow, we're moving coulombs around. So don't confuse with electron motion. And this is something you just got to get straight in your head at the beginning, and then go to a little overhead for this. So just keep repeating to yourself as we go through this. We're talking about moving positive charges around, which they're not actually moving. The electrons are what are moving, which was taught about in physics. But unfortunately, we'll go to our little thing. This is in your book. Franklin derived equations for something that was unknown. And when he did it, he assumed these unknown items had a positive charge. And he was deriving all the base equations of circuits. Awesome. And he derived all these equations, and laws were built on them. And then Thomson said, hey, but you know, look at my experiments later. Electrons are actually what's moving, or the propagation of motion from there, from electrons moving around. So, in reality, in life, in the very small level, electrons are actually moving. All your equations and circuits don't assume that. They assume that actually positive charges are moving and they're going the other way than electron motion. So everyone just went with, all right, these equations are already derived. We're going to assume positive coulombs are moving around. So when I'm doing examples, when we're talking about things moving around, all these equations are derived upon an incorrect assumption that positive items are moving around, but just so you know that. So if you're really into physics and modern physics and electrons are moving, just suspend your thought process for that and flip everything around. But as I go through, I'm going to do everything, talk about all the examples that positive charges are moving around. So you're going to have to pretend a little as you go along there that positive charges are moving around. And I'm just going to start my theory and my drawings and everything of a circuit and have my little ping pong ball coulombs and show them moving around, and we're going to talk about things gaining and losing energy as they are these positive items moving around. All right, so let's start our derivation then. So we have a mystery potato circuit, and in there are some interconnected series of things taking energy, giving energy, everything and whatnot. And off of there, we have a little wire coming out, and we have some current flowing through there. When you start drawing these arrows or see these arrows drawn, it's kind of assuming there's some current flow direction. And we'll say in this case we have 2 amps of current flowing that way. So what the heck does that actually mean? So part of what I want you to get out of this as engineers is to know, okay, it's not 2 amps, I solved the problem, woo, we're done. What does that mean? So following our positive theory, what it means is that any point along this wire, so that we're assuming wires that have no resistance in them, they're magical conductors. For 2 amps, there's 2 coulombs per second going from left to right through here at any snip along this wire. So who knows what else is going around here? It's some black box. We'll solve for that stuff later. But in this breakout, I could read, put a meter in there. I have a 2 amp reading. Any given second, I have 2 coulombs going past there from left to right, because this is a positive value, and we have our arrow drawn left to right. If you start seeing things that have a negative current number on there, so we have our mystery potato circuit. We've cut a piece of wire, or we have a piece of wire coming off across there. We're going to assume there's some current flow. But when we put our meter on there, it reads -3 amps. If you get a negative reading when you're doing something like that, it means the current was actually flowing the other way. So at any given second, you have 3 coulombs going from right to left across there. Even though this arrow is drawn, we were just kind of assuming a direction. When you get an actual readout, if it's negative, it really means the current was flowing the other way. So current, and a lot of these things in here are vector quantities. Not in the I need Cartesian coordinates vector sense, but that you have a flow direction and a magnitude. So when we're looking at these items, you're going to have vector quantities. They're going to have some amount of coulombs per second and a flow direction for right now, but we'll also have voltage quantities. So just an equivalent circuit is if I had the current flow drawn this way, and I said this is +3 amps, just that you can recognize these 2 things are equivalent, because we're dealing with vector quantities of the amount of flow and the flow direction with the signs for negative versus positive in there. So vector quantities, magnitude and direction. Starting with current, and this is the one thing your book is really good at, I want you to start to get an engineering feel for numbers. Not like I know what current is, but how much current should I really expect is something? If I accidentally grabbed the power source of something, would I fry myself? Kind of quantities. So engineering feel for current. So current quantities can vary greatly. Let's see, 1, 2, 3, 4, 5, 7. Let's see if I can do this right. 1, 2, 3, and then 4 is close. 5, 6, 7. And let's just talk about some things you might encounter. So 20 milliamp level is like a little LED light. So you have LED lights all over the place. They use less current, they don't heat up too hot. But so you start to get an engineering feel for things. You need about 20 milliamps you'll have going through an LED. If you're surfing the internet on your phone during my class, you're using about 200 milliamps to run that thing. If you are plugging in an old school 100-watt light bulb, which you can't really buy too much anymore, but those old light bulbs uses about an amp. So you can see why in industry now they're making more LED light fixtures instead of the more traditional ones. You're using orders of magnitude less current through them to do that. If you're surfing the internet on your laptop during my class, you're using about 2 amps to do that, to run that. If you're going to go microwave some lunch after this, you're going up to about 10 amps, so an order of magnitude larger than an old school light bulb. If you drove here, your car starter needed about 200 amps to get going, so that's why the starter is really important to get that flowing through there to make the electrical connection through. And hopefully you never really get hit by lightning, but that's lightning. It's about 1,000 amps. So going an order of magnitude over. So part of what your book does a really good job at, and I want to try to embed in you, is we got to solve problems. But if you walked away and someone said, like, I made this thing, it uses 1,000 amps, you're like, no, this doesn't even make sense. So as engineers, you should start to get those engineering feels for what things are running and how much to expect out of things. So let's see, we talked about current, we talked about charge. Then there's this guy called voltage, and he's related because you need voltage for current to flow. So in order for electrical current to flow from one point to another, you have to have a voltage difference between those 2 points. And the voltage difference acts like the potential for current to flow in a certain direction. So I'm going to write that out. In order for electrical current to flow, from one point to another, a voltage must exist between the 2 points. So voltage is always a relative measurement, either between 2 points or across an element, like what's the voltage drop across, we'll talk about these, across this resistor or across this capacitor. So voltage is a relative measurement either between points or across an element. So you should never say, like, in this circuit, at point A, the voltage is 10 volts. No. The voltage at A relative to either ground or across the element that was on the other side of A could be 10 volts. So we're going to introduce a new term here. He's voltage. His big symbol is V. His little symbol is also V of t, which I'm going to try to always say these things out loud and try to not make this look too much like a cursive R. But if you're looking at my notes later and you're like, what's this cursive R? That meant I wrote V too fast. So V, or V of t, units, volts, which is a joule per coulomb, which is a Newton meter per coulomb. And in short terminology, what a volt is the energy to move a unit charge between points. So 1 volt is the energy to move a unit charge between points. All right, so we're talking about energy. I'm going to do energy or work as the next term. A lot of your majors, mechanicals, the aeros, the civils, the industrials, you're really going to be talking about in practical applications where you start to use circuits, moving energy, creating energy, storing energy for chemicals. So what it comes down to for your applications in these majors is what we're doing with energy. How to save energy, how to store energy, how to create energy. I need more energy over here. I need to save this energy for later. We're all moving around energy within most of the majors in this class. So for energy, so either work or energy, we're going to use the interchangeable ones in this class. Work or energy is our term. We're going to use big W, which would be little w of t. He's a joule for his units, which is a Newton meter. So I'm going to leave this up here, erase this side so I can draw a little drawing for you guys. So a lot of what I want to do at the beginning is just make sure you get a feel for that positive elements moving around, what things mean. So I'm going to do just a couple little drawings that relate to some of that stuff. So we have our circuit. And who knows what's in this part of it? Some motors, some batteries, some whatever, solar panels. But then we're pulling out a portion of that circuit. And remember when we said we read a voltage, it's got to be either across an element or between 2 points. And we're going to say A up here is designated as our positive terminal, and B is our negative terminal. And when I put a voltmeter on here, I'm going to read 2 volts across there. And remember our units for volts is 2 joules per coulomb. So what the heck does that mean? So I read 2 joules per coulomb, and I have positive up here and negative up here. So if we have positive at A and negative at B, and we have a positive voltage reading across there, what we start to want to look at is potential for current to flow. And in doing that, we have a positive value up here, a negative value down here, and a positive value for a voltage reading across there. We can say that this side is at a higher potential, and this side is at a lower potential relative to coulombs moving around, relative to current flow. And so if I took my coulomb, and he started at point A, and he went through his whatever's going on in our black box circuit, and came out at point B, he'd be starting at a higher energy level. There's still just one of him per second, some coulombs per second. He's here, he's at a higher energy level. He's got a whole lot of energy. He goes through here, something in here uses some of that energy, and he comes out at a lower level. And he comes out, a single coulomb, at 2 joules of a lower level, because it's 2 joules per coulomb. So for every coulomb that goes through here and comes out on the other end, something in this circuit has sucked up and used some of that energy, and used specifically 2 joules from each one of these. So we're not creating or destroying these guys. But he's really energetic, woo! He goes in here and maybe like an LED or a motor or something sucks some of his energy out, and then he comes back out to this point, and when we read him over here, he's at a lower energy state. So what I want you to start to understand is if we're moving a coulomb one way, and he goes from a high potential to a low potential, he's just losing some of that energy, and based on the voltage amount, you know how much energy is lost per coulomb that's going through that circuit. Does that make sense? You guys good with that? All right. We're going to draw 2 little scenarios down here. So let's draw 2 little comparator scenarios. So again, one big thing of mine is for you to understand what's going on with these. So if we have 2 potato circuits, I don't know what's in them, some mystery elements. But at this point, there's only a certain spot you can start making readings on them. It's convenient to get your voltmeter in there as an engineer and read out at these specific points in your circuit. And again, this is positive terminal, negative terminal on this one. But now when I read out, I have a reading of negative 5 volts. And it's still a point A and point B. So this was the positive terminal, that was the negative terminal. I put my voltmeter on there in that configuration. Oh crap, I've got a negative reading. If you have a negative reading, what it really means is that this side down here is at your higher potential. And this side down here is at your lower potential. Because while these are designated positive and negative, when you put your voltmeter on there, really, remember the voltage difference is the potentials for the coulombs to move around, the potential for current to flow. If this is negative, it really means the lower potential is up here. And if you took, where's my little guy, a coulomb, and you had him over here and he flowed through the circuit and came out here, he would lose 5 joules of energy going from B through whatever items were in your circuit out to A. In comparison, if now we flipped where these terminals were, and we said A is our negative terminal and B is our positive terminal, but we had a positive 5 volt reading across here. Since it's positive 5 volts, we don't have to flip for anything like that. We can just look at the signs on here. So since he's positive, he's really the high potential, and he's the low potential up here at A. So these 2 end up being equivalent. So what I want you to start to get a feel for is voltage change across 2 points is the potential to move current around. What does it mean when you have a negative reading? Well, it's really the potential is the other way to move things. And even if this was designated as a positive terminal, he's really at the lower potential due to this negative reading. Positive reading, it's really how these guys are tagged and which way the current will then flow, and then what happens to those coulombs as they go through there. If we're going from high potential to low potential, it's losing energy to whatever is in the circuit. Something in there needed it to do something really neat that you designed it for. So this goes back to these are vector quantities. You need magnitude and direction. I'm going to erase this board, but then I'm going to go to the overhead just to show you a little built item in here. All right. So I have a little guy here. I'm just talking about potential again. I need to grab a pen to point with. I'm going to try my best to bring something in every class, and some of them might look very childlike. They're these little snap circuits or little bit demos, but they're easy for me to build before class to show some of these principles. I'm also going to try to bring in something, we'll talk about it next class, that's an inventor's kit, which is actually an Arduino board that you can build circuits with that next semester they're going to be required to buy as a book, so every student in a class will have it, but I couldn't change your textbook requirement, so you guys don't have to buy it, but I'm going to try to do the demos that are in there this semester. So I'm going to try to do some demos every class to show these things. So we're talking about potential and a complete circuit and elements in a circuit. Now we're going to talk a little bit more about looking at a physical element to what a little drawing might be to what our circuits class drawing will probably look like. So for this guy, we have a battery. He's something that can generate energy. He can usually get those coulombs jazzed back up. They go in one end, you come out the other end, they're at higher potential to do some sort of work. So all you chemical engineers out there, if you do any research into battery design or energy storage, that's a good place to tie this class in. This is just a power supply switch, so I'm going to turn him on, but he's not the switch closing the circuit yet. So I have my battery. Something flows through him. He'll go from, a coulomb goes through there from low potential through the battery to high potential. So in that negative terminal, through here, chemical reactions going on, gives it some juice, back out in a higher potential level. And we're going to flow through to this point, and I have a little switch. So I have a switch here that I'm going to close. Only when that switch is closed can then current flow to go through there. So you need to make sure you have nothing open in your circuit. Then current can flow, and we're flowing coulombs current through this direction. Remember, we're assuming positive coulombs going through as our current flow direction. And then we have something here. This is just a little LED that uses some of that energy. So we have an element. We're going in one end of it at a high potential. Each coulomb goes in with some potential, and it's coming out at a lower potential out the other end. So as he goes through this light, he's at a high potential, he comes out at a lower potential, and then he flows back through here to the other end of the battery. And it's a complete circuit. I'm slowly using up the chemical energy in here to make this light to go through here. And these elements, we're going to talk about, solve for element 1, what is it doing? They're going to either be supplying energy, like a battery, or absorbing energy, like a light, or, I don't know, let's see. Stick a little motor on here. Little motor. Let's see if I can get the fan to work. I have the horrible, luck of putting chalk on these usually, and then they don't work. Or a little computer fan. And each one of these is sucking some of that energy out, and then it's going back through, and this chemical reaction is giving some energy back to it. So that's what a physical entity looks like. This is a little sketch if you're trying to figure out what's going on. But when we go to actually looking in our course, just the beginning, we're going to have mystery elements. And they'll usually have these boxes and maybe a number in them. So this is element 1. So he's a battery. He's going, as the coulombs go through, they're going from low potential to high potential. And you want to know what the element's doing. Energy is being supplied by that element to the coulomb. So he's a battery. He's supplying energy to that coulomb as he goes through there. Element 2 is something that goes from a high potential, high energy state to a lower potential because that energy is used to do something in him. So element 2 is going from high potential to low potential, and the energy is being absorbed or used by that element. So I'm going to put these in a little box and send them around if you want to play with them. But then what I'm going to do from here is take this and draw it up as what you might see as some of the beginning circuit problems we do as a sample problem on the board. So just send these around, you can play with them, and then just make sure I get them back somewhere near the end of the class if you want to. So that's going to what a circuit drawing would look like for something like that. We'll do one little problem. And again, what you guys are looking for a lot of times in your majors are applications of energy, or more directly power, and we're going to drive this first simple power equation with this problem. You want to know how much power is going on, either being absorbed or supplied by those elements. So if I redraw that little circuit out, we had element 1, we had an element 2 over here, and it went back around, and we had a 9-volt battery, and we were going, our current flow direction, as we talked about him flowing, positive current flow direction was that way. We went across the battery, we went from a lower state to a higher energy state. So we're going low to higher energy state. My coulombs. He's got a higher energy state. He goes through here, and we put either a light or a motor or a fan or something in here. So he's at a higher energy state. He goes through, he makes light, he makes motion. He comes out at a lower energy state. So we go from a higher energy state, oh, I'm too short for this, to a lower energy state. Y'all never usually write up there. Right now, this circuit is something called series, and we'll talk about series and parallel later. We have a single loop. If a current is flowing here, the same current is flowing through all of these. We're not changing that current amount. There's nowhere for that current to flow off or go somewhere else. And this we'll talk about a little bit in the water analogy. You kind of think of current flow like water. There's only one pipe going around here, so that same current's flowing through. In my office, I put a voltmeter, a current meter across there, I read 3.5 amps. So we have 3.5 amps flowing through, powering up our coulombs across a 9-volt battery, and then using them somewhere over in whatever you plugged in there. So we're going to go through and talk about the power going on in these elements. In order to do that, you need the power equation. So I'm going to introduce a new term for you, which is power. So power, either big P, or if he's a function of time, little p of t, his units are watts, which I'll never forget because in 7th grade, I had a physical science teacher who spoke really fast. And he'd be like, joules per second, what? Joule per second, what? And I can't believe he was so corny. But I'll never forget that a watt is a joule per second, because he kept making us say, what? What are you saying? And so it's joules per second's what? And I'll never forget Mr. Nesmel, 7th grade in Tampa. Oh, I grew up in Tampa. Awesome, awesome teacher. So from that, our power equation, you're going to see him boxed. He's one of those ones we'll use. P equals IV. All right. And if we just look at units, I'm a unit freak. I like to cancel out units. I used to do like Math League and all kinds of fun stuff in high school. So I love to do my units when I'm looking at a power equation, like we have amps times volts, which would be coulombs per second times joules per coulomb. I get to cross something out. Sweet. Which goes to joules per second, which is where you can really confirm you have watts. Yes. Power equation. All right. So we have our power equation. Now I'm going to step back to our drawing of our element. And you might get a question like, what is happening in element 1? Which is kind of a vague question. They'll get a little more specific when you actually have to provide answers, but I haven't shown you that format yet. So what is happening in element 1? All right, well, let's talk about him. So element 1, we have positive 9 volts. We have a positive current flow direction. We're going from a lower potential to a higher potential. So this element itself is supplying power. So supplying or absorbing becomes the vector component within these types of problems. Tell me about the power through element 1. He's some amount of watts either being supplied or absorbed. So when you give answers on these things, you need to know if it's something that's providing energy or sucking away some of that energy. And then you want to know how much, and for that you use the power equation. So what's happening in element 1, we're just going to go through and use our power equation, P equals IV. So we have 3.5 amps, which we saw flowing through there. So series or only current going through there is 3.5 amps. He's a 9-volt battery. It ends up as 31.5 watts. But that's not the answer and what's going on there. You need to be able to talk through and see if it's being supplied or absorbed. So you need to go through and look at that positive current flow direction. This is a decimal point. Positive current flow direction going from low potential to high potential. He's 31.5 watts being supplied. So element 1 is supplying 31.5 watts. That would be something that would look like a traditional answer to some of the beginning problems, and we're going to do more samples of this. But generally, to summarize for today, when we're talking about supplying or absorbing, is if you know positive current flow direction, so across elements, with positive current flow direction, if you're going from low potential to high potential, that element itself is supplying power. It's giving those coulombs more energy to do stuff. So element supplies power. Or or if we go from high to low potential, that element is going to absorb power. So for you guys in engineering applications, these are your batteries, your solar panels, your generators. These are your light bulbs, your fans, your motors, your whatever you might be doing work with. And what I want you to understand is when you're building a circuit and you're analyzing one, what the heck was going on there? That was a supplier or that was a taker, an absorber. So what we're going to go through next time is something called Teligens's theorem that says when we have a more complicated circuit, the suppliers and the absorbers have to balance out. And we're going to do an analysis of multiple things, how to look at them, and then do a math check using this theorem saying all the suppliers need to give as much power as all the absorbers are using when you start doing problems, which becomes a good math check when you're doing other things more complicated later in the class that supply and absorb should always check out. So if you have time in an exam, you can always check your answer that way.